Hey everyone, my name is Yulia Kizilbasheva. I'm a graduate student at DePaul University, and this is my presentation for the class CSC 4A1. The paper that I decided to review is called Learning Phase Age Progression, a Pyramid Architecture of Generative Adversarial Network. It was published in the Digital Library of Institute of Electrical and Electronics Engineers in 2018. Before we start, I would love to talk about some important terms that we're going to use throughout this presentation. So first of all, image processing is the process of transforming an image into a digital form and performing certain operations to get some useful information from it. Age progression is the process of aesthetically rendering a given face image to present the effects of aging. And finally, convolutional neural network, or CNN, is a type of artificial neural network used primarily for image recognition and processing due to its ability to recognize patterns in images. So basically, this paper introduces a new approach for face age progression. And in the late years, it was evident that agent accuracy and identity permanence requirements were not studied enough. So the proposed method mainly focuses on creating those realistic agent effects. The proposed method is called GAN, or Generative Adversarial Network. And why is this method good? Well, first of all, it integrates face verification and age estimation techniques and simultaneously addresses agent effect generation and identity cue preservation. Secondly, this method emphasizes the importance of the entire face, including the forehead and hair, which significantly impact perceived age. And lastly, it introduces new validation experiments, including commercial face analysis tool-based evaluation and sensitivity assessment to changes in expression, pose, or makeup. So before showing the experiments using GNNs, the paper provides information about previous approaches for face age progression. Number one shows us that talks about early models, and mainly the whole idea is that initial approaches used physical models to simulate aging mechanisms, including cranium and facial muscles, and different methods like cardioidal strain transformation for head growth or 3D layered dynamic skin model based on the skin's anatomical structure were proposed at that stage. Second, we can see that we advanced to the data-driven approaches, and basically they were focusing on learning aging patterns from training faces. We learned about methods like prototype-based method, considering illumination factors and multi-attribute decomposition. Recent attempts involve deep generative networks. The examples are conditional adversarial autoencoder or temporal non-volume preserving, or TNVP, aging approach. So pretty much those methods achieve short-term progression, but they all lacked individuality information that led to variations in color, expression, and identity in synthesized faces. And now we're going to talk about GN method that overperforms all previous methods. So GN has a generator and discriminator parts. And I'll move to the slide with the image that demonstrates the whole process. So generator, or G, employs a CNN-based generator for age transformation. Generator involves striated convolutional layers, residual blocks, fractionally striated convolutional layers. The emphasis is on entire face synthesis that leverages convolutional kernels and instance normalization. Discriminator, on the opposite, or D, helps to explore data density of faces from the target age cluster. Also, it minimizes least squares loss during training for GAN and includes both real and generated faces as negative samples. To address the issue of identity preservation, GAN utilizes deep face descriptor network, which encodes the personalized information and further defines the identity loss function. And from this image, we can see how it works. Additionally, they used a function of a pixel-wise L2 loss in the image space, which was adopted to further bridging the input-output gap. In that formula, X denotes the input phase and W, H, and C correspond to the image shape. They also used the function that we can see below that was used specifically to calculate the training loss. So now let's see how they tested the GAN method. During the data collection phase, they used MORPH mugshot dataset and cross-age celebrity dataset or CSCD for training GANs. Additionally, FGNet dataset was also adopted for testing to ensure fair comparison. And on this slide, we can see some of the implementation details. So faces were aligned using eye locations provided by datasets or detected by Face++ API. They used 163,446 face images from Morph and 51,699 face images from CACD. Those images were cropped to 224 by 224 pixels, and only one adult agent was considered. Then they did 3 separate training sessions for different target age groups, and they specified networking architectures and trade-off parameters. Finally, training details included Atom Optimizer, a batch size of 8, and 50,000 iterations. There were 2 experiments, and the first one was conducted to test age progression. In the first experiment, the researchers used 5-fold cross-validation on CACD and Morph. Agent effects turned out to be visually plausible, including variations in race, gender, pose, makeup, and expression, which we can pretty much see from the image on this slide. The second experiment's objective was to test aging model progression. And the results have shown that age-progressed faces maintain photorealism and fidelity even with variations like glasses, occlusions, and pose changes. Additionally, it showed that hair aging was also considered, showing wispy and thin hair growth. Additionally, researchers used Face++ for age estimation. Estimated ages were well matched with real images, as we can see from the graphs on this slide. Also, researchers used Face R plus in this case. As we can see from the results, mean verification rate is high, which confirms identity preservation. However, verification performance decreases with increased time between images. This result shows that visual fidelity and quantitative estimations indicate superiority of pyramid architecture over one-way discriminator. So at the end, they also decided to perform a human observer evaluation with 138 paired images of 54 individuals. It showed that 69.78% of people who voted were in favor of the proposed method, meaning GANs. 20.8% voted for prior works, and 9.42% said that they didn't really see any significant difference. So, all in all, researchers proved that their proposed method, namely a generative adversarial network, showed a way better age transformation accuracy, better identity preservation, And the biggest difference from other methods was that it generated signs of age using pyramidal discriminator. So yeah, this is pretty much it. On this slide, you can see the information about the research paper and a link for it. Thank you so much.